because I have used Explainable AI in some of the multidisciplinary projects that I'm part of. I want to share some case studies and some of the learning from my own experience based on that. So today's talk is slightly organized in a way. I want to start with a little bit about me, what projects I was previously part of, and then quickly move on to Explainable AI. Bit of technical glitch. My clicker is not responding properly, but anyways. Okay, thank you very much. So I'm currently part of a multimorbidity research project, which I started in University of East Anglia, which is in Norwich. So this is a multidisciplinary research group that is focusing on inflammatory drivers for shared long-term disease trajectories. And we had an NIHR stage 1 grant to do some proof of concept study, and there is a stage 2 grant going on. So I was leading a work package that is actually taking in electronic health records where the patient's longitudinal data was captured, and using the follow-up information, what we developed is a neural ODE and CDE networks for multi-stage survival analysis and disease progression modeling. The types of data that I was using to develop these solutions are mostly the CPRD data, UK Biobank, and Norwich has its own 25-year longitudinal cohort study data on Norwich arthritis registry. And what we proposed for the stage 2 proposal is more or less in terms of, along with the development of the neural ODEs, which are continuous hazard function modelers based on the time series data we are feeding from the electronic health records. We also wanted to highlight the fact that whenever we are using deep neural networks, which are complex in nature, we also need to, because these are quite sensitive applications where we are dealing with patient data, we want an explanation module at the end where we were generating counterfactual explanation by perturbing the input dynamically, because time series data is longitudinal in nature and contextual information is quite important in this case. The second set of projects I was involved in Norwich was also a collaboration with East Anglia, University of Oxford, and Middlesex University, where it was a Cancer Research UK funded project where we were processing endoscopic video data to detect esophageal cancer. So Oxford University Hospital provided us with a small 20-subject data set where we developed multiple algorithms for, let's say, region segmentation. And we managed to achieve about, let's say, 85% accuracy in identifying various stages of esophageal problems, such as Barrett's esophagus and, say, suspicious or cancerous regions in the disease data set that they have provided. With this, we provided the university hospital with an interface where the clinician could include the additional test data they have in the system. So there was a user interface design where they could retrain the model and test the interface as well. So I was part of a postdoc as a postdoctoral researcher. In the University of Manchester, I was mostly doing wearable sensing. So as part of a machine learning developer in that research group, what I did is mostly sensor data analysis. And the data set we were using based on human activity recognition. So let's say a person is monitored using a wearable sensor for 24/7, and you monitor what that person is doing over the entire day. So what we developed is an activity classification interface, and the project that I was part of was called the Wearable Clinic. So what we did at the end is we did real-time human activity recognition and phenotyping, and we deployed models for individual or personalized model on a wearable sensor. So my experience of, let's say, deploying models on edge or low power computing interface came from this specific project. And I'm still quite interested in deployment stage on device and so on. So as I'm a new academic member of staff here, I would probably be recruiting some PhD students that work on, let's say, quantization of the model developed models that are able to fit in low power and, let's say, low resource computing devices. This is one of the projects that I was very recently part of during COVID period. So this project was mainly dealing with automated gesture and video analysis and the application that we were developing. So this is a collaboration with a company, spin-out company we had at the University of East Anglia. So they were developing a remote proctoring solution. And during COVID, let's say, high-stake assessment platforms. So let's say somebody is taking a certified insurer's exam, not in an university setting, but if somebody is getting a certification from one of the qualifying bodies, then they want the monitoring to be very accurate, and you want to identify whether there is any cheating happening in the room that you are in. So what we did based on, so Chartered Institute of Insurers shared us with a 340 participant data set. With that, what we did, we have done real-time analysis of gesture, eye movement, facial expressions, and that provided an interface that could generate some anti-cheating proctoring report. And we also looked into, because we are part of a university environment, it was also important to look at whether because you know that exams are stressful scenarios, you also want to know whether any of the test items that is being presented to the student that is taking the exam, whether it is affecting the students in let's say, one of the problem is harder, whether it is affecting or stressing the student enough at that specific point of time. And the solution, because let's say whoever is taking a qualification exam, if the interface is online, it is remotely being proctored, you could also need the solution to be inclusive. So the facial landmark detection or hand gesture recognition techniques that we were doing for this analysis, these are pre-trained model. And as you know, algorithms are as good as the data that you have trained it with. So we needed quite a bit of tweaking and tailoring so that every participant from any race or ethnic group has a robust and inclusive, let's say, performance coming out from the system and so on. And we focused quite a bit in terms of AI audit for this system, because the selling criteria, unique selling point that we are having for this product was that we are providing robust and inclusive solutions. So we did a step of AI auditing through the system, where we are presenting the system with, let's say, various, let's say, failure groups that may be failed by the system. And some of the things also came up during this development was, let's say, every participant has different expression to a stressful scenario. Somebody is probably expressive enough so that you can see the stress clearly. There will be some people who would not show anything on the face and so on. So given that I worked in quite a multidisciplinary environment, and my main research track is AI for healthcare. And oftentimes with the projects that I worked in, we had, let's say, patient and public interactions. You would see that people, the medical professionals that are partners to our project, or the patient participants that we had in the project, there is a lot of mistrust on automated systems. So they are not quite sure of what machine learnings are doing on the back end, or the decision-making process are not as clear as they should be. So based on those findings, I spent, let's say, one of my major research direction is in explainable AI. What we are trying to do with explainable AI is to bring better understanding to the black box models or the complex models that we are employing to solve various automated problems right at this moment. So you may ask, let's say, why model understanding is important. There is a commercial drive based on many enterprises currently rely on automated machine learning models to make important decisions. So one of such applications could be, let's say, when you apply for a loan or when you're applying for a credit card, your application is being assessed by an automated system before it gets assessed by a human user. Or let's say we are using diagnostic image processing tools to identify whether there is a cancer or whether there are, let's say, non-cancerous cells and so on. So these are quite high-stake decisions. You need them to be as accurate as possible. And there is a technical drive. So let's say if I say my model is 95% accurate, there are 5% of the time when the model is not doing okay. So those are the model's failure scenarios. So you need to know the edge cases or the circumstances of the failure quite well to be able to, let's say, have a post-processing scenario where you can do something where the system is failing. You can either come back to collect more data on the cases where the system was failing and so on. And if you know why the model was failing in specific scenarios, you can, let's say, learn more about the problem and the data, and hence you can improve the model's performance in bringing in some additional measure. And let's say, in terms of social and ethical aspect, as I said, machine learning models are as good as the data it has seen. So in case there was a discussion we were having that day, so let's say if a homeless person whose detail is not in any system at all, will that person be equally treated, or whether an automated decision-making system can treat that person's information as sensitively as it should be dealt with? So there may be some biases which could really harm vulnerable group of people. So we need to make our models or document the data that we are training our models with quite systematic to see that what the models are capable of actually, because the data that it's in, the decision-making process are based on those set of data, and we have to document that process quite rigorously so that we can say that our model is representative of this type of population, and anything that is outside of that scope needs to be treated separately. So this is a way of, let's say, maintaining fairness in a scenario where we are employing automated decision-making systems. And if we have a system that is explainable, or if we could understand the decision-making process of the model, it's easier for humans to trust a business that can explain its decision. And there are a number of regulatory aspects that we need to be careful of. So in recent years, most of the countries are bringing laws and acts to deal with any algorithmic decision-making system. So UK has Center of Data Ethics and Innovation, who has released an AI Assurance Guide in 2021. European Union has, let's say, a draft AI Act that got released in 2021. So whoever is employing an AI-based decision-making system now has to comply with the regulatory requirements by, let's say, various countries that are using that specific system. USA had some of the laws that are already in place. So there is Algorithmic Accountability Act of 2022. The New York, right at this moment, their Department of Workers and Pensions has a law that is in place. Let's say if one of the workers that has been processed by an automated system is, let's say, misprocessed by somehow, so that person was supposed to get a job, he did not get a job because the data was misprocessed by the algorithm, then for every mistake that the system has made, the company that is using that algorithm has to pay, let's say, $1,500 US as a penalty. So if the system has made 10 mistakes in a month, it will be penalized as a part of the AI auditing process and so on. And there are various standard bodies that is dealing with these regulations and so on. I think I had one slide at the beginning. Prior to this is, let's say, McKinsey Global Institute simulated and reported the impact of AI by 2030. And if you look into the list of, let's say, which domain would generate the economic, let's say they will grow economically because they're processing whatever data they have, and they're using the information quite properly, or using the insights from the user information that they have. They are now, let's say, managing their resources better, and they're generating more revenue. And in the list, if you say that healthcare systems and services, it is coming on under, let's say, 5, 6, 7 industries after those industries. And this is because, let's say, at the pace of adoption of any AI-driven system, trust is a quite important factor in that technology is being adopted in that industry. So as healthcare decisions are quite high-stake decisions, whoever is making those decisions has to whatever they are using in that system. And you would see that these safety critical systems are adopting AI slower than any other industry. Let's say if you're in a retail industry, if you're processing user reviews and things like that, and depending on that, you're making recommendations, making more sale and so on, you would see that those are not as severe as, let's say, you deployed an AI system that was supposed to detect cancer and you missed a cancer patient. So that has a different consequence than a simple automated decision-making system of a recommender system. And explainability of the models that we are building, it could actually provide some insights in how the decision-making system was working in practice. So for UK, I probably have a slide on what that recent release from the Center for Data Ethics and Innovation. And they suggested, let's say, every software, if you look into the second column for the diagram that it is going there, to assure any user of the AI system, they are going through some assessment by the Medical Health Research Association. And any software AI that has to go through medical device regulation, and like various solutions that are coming under various disciplines of these or rules or principles of the UK law has to come, let's say, go through various authorities that will approve the solutions that we are developing for the application areas of interest. And as I was just talking about why model understanding is important, so an AI system has various stakeholders that are using that system. So let's say if I'm an algorithm developer, my interest would be, let's say, if it is a black box model that I have developed, how do I debug it? Or what are my failure cases? How can I improve the performance? So the example that I'm showing on the screen is for a financial organization where a customer could apply for a loan and so on, and the model is deciding that this person is not being granted a loan. So what you would know, what the stakeholder as a bank customer would want to know is, why was I denied? Like, why did I fail, or what can I do to improve the scenario so that when I apply next time that I get a loan? And as a financial investor, bank will want to know, if I'm investing, if I'm providing loan to this person, whether this person will be able to pay the loan back and so on. So the next few slides are some examples like this, where we are saying that, okay, John, the bank customer in the previous slide, was denied the loan. With model understanding, if we could explain that, okay, model is using this feature as its predictor of whether this person will be able to pay his loan, then you can suggest the customer, okay, you need to increase your salary by this amount. You have to pay your credit card bills regularly. So these factors will switch the model's decision for you to get the loan and so on. So the loan applicant will get some information about how he can be successful in this automated system. The second example, as a debugger or algorithm developer, I'm using an example of, let's say, there is a Serbian husky, which is lying on snow, and the model, let's say, correctly predicted this is a Serbian husky. So if you visualize the attention areas for this input image by the predicted model, you will see that the information this model has used is the snow only. Nothing about the husky was processed by this model. So what you would need to see as a developer, so when you are auditing your system, when you are testing your model properly, it was a right prediction, but the reason that the model was using was a wrong reason. I don't want the model to process anything of the husky by processing the information or features about the snow only. So it could be a plain snow and the model will predict that this is a Serbian husky, but there is no husky. So if your model is relying on incorrect feature, if you know how the model is behaving with various sets of input, whether the right set of features are being processed by the model, then you can fix the model if you know what's going wrong in the model. And another sensitive use case could be, let's say, we are processing the defendant details, which is maybe free text written by various groups of, let's say, police department or crime investigation department. And a predictive model decided, so this is an example of an automated system that is currently in place in one of the US states, where, let's say, they process the defendant details, and the prediction in this case is, okay, the detail for this person, whatever they have seen, this person is risky to release on a bail. But when you looked into the model's understanding, you saw that the reason for somebody not being released on bail should be the severity of the crime. So the features that the model has processed in this case is, let's say, it is showing a feature importance that race and gender is governing the decision of the model. Crime is probably a less important feature for the participant that we passed in by the model. So if you can visualize what features were provided more importance, you can decide on whether that this prediction is being governed by race and gender rather than crime. So this is probably not a suitable model for processing defendant details if the feature importance for the model is not the right set of, again, this is probably, it could be that this person is actually risky to release, but if the model is not dealing with crime as its major factor for deciding whether this person should be released or not, it's not the right model for this purpose. And if we know the failure cases, and as I said, any AI system has multiple stakeholders that are deciding on various factors. So if this is a healthcare model, and if you, when you are trying to investigate how the model's decision-making process is working, and for this corresponding example, if you, when looking into the rules, so let's say this is a decision tree-based model where when it was being examined for gender male, you would see that when called for the gender of male, it is using the right set of things. Let's say this person has cold, this person has cough, and then this person is sick. But for the female group of participants, I divide that when it is deciding that this female is sick, let's say ID number, which has nothing to do with somebody being sick. So in that case, you don't know that if the decisions are not looking right. So you either need more supporting examples to be added in the data set, or you need that feature which has nothing to do with predicting whether somebody is sick and not sick. You need to drop it during the model training phase. So the models, we need the models to be as accurate as possible. And with accuracy, over the years, what we have done is, let's say we initially had, let's say, very simple, intrinsically interpretable linear models. And we have developed, let's say, to keep the interpretability still manageable, the decision trees were, let's say, developed. And then as we are developing more complex models, such as ensemble models, such as random forest, or if we're developing neural networks that can, let's say, can be tailored to any decision boundary that we are getting, you would see that the interpretability of the models are reducing as we are increasing the complexity. So there is, you either need to choose either very accurate models, but you're losing the interpretability. But with present day tools for explainable AI, you can come onto a trade-off. Okay, I want this accurate model, but I still want to have interpretability. So what the developers of recent day explainable AI tools are saying, complex models are inherently complex, but what we can try is, if we can break down a single prediction, it is only a small part of the overall complex model. And if we are dealing case by case, or if we could group together similar sets of decision in small branches, we could probably still explain the complex models that we are developing. So we then get accurate models. We have the explainability aspect of it dealt by dealing single prediction one by one. The tools that's available for explainable AI are the so any linear models or tree-based models have explainability included in their design. So if you say my output predictor Y is mx1 plus m2x2, where m is coefficient and x1, x2 are my variables. So if you know the coefficients, you know that how they are being processed by this model to produce the output. But as I said, with complex models or black box models that we are developing nowadays, the types of input that we are putting in, the algorithms are creating a mapping function from the input domain to the output domain. And what we are doing is we are doing post hoc explanations. Once the model is developed, we are having an explainer module to break down how input is being processed by this black box model. And based on that, we are generating some explanations. So in the rest of the talk, what I would mostly focus on is the classic shape values to discuss some of the case studies. And with Sharp is a tool set developed from game theory, and the tool that I'm going to use in the next slides are a group from Microsoft, and Sandberg's group has publicly made the toolbox available for anybody to use and explain for black box model explanation. So using Sharp, in recent years, there is another open source toolbox called Explainer Dashboard. So they have combined many of the methods or APIs available from Sharp to create a holistic explanation dashboard for any model that you're developing. In this slide, I do have a mention of the DICE toolbox for counterfactual explanations. So I've tried to show one or two slides because this is one of the types of explanation I use with electronic health record models. And for image processing, you would see the types of explainabilities being brought by using the saliency maps, class-wise activation maps, or GradCam++. So a little bit of background on Shapely values. So this is an open source library for, let's say, calculating Shapely values, which are kind of feature importance values for the that you are using. And the toolbox is bringing some key contributions, such as the quite efficient algorithm developed to calculate shape values for tree ensemble models. And the API that they are providing to explain tree-based model is called tree. They have a fast and good approximation algorithm for deep learning models, and the way they can explain deep learning models, the API they are using is called Deep Shop. And you are going for a model agnostic model. The methods that they have developed at the library, they are slightly slower, but the accuracy of the calculation is quite accurate. And the API for using any model agnostic is Kernel Shop. So if you have an SVM model and if you want an explanation out of that model, Kernel Shop would be your API to call to explain the decision-making process. And it works with linear algorithms, tree-based or deep learning models, and you can have a multi-stage combination of any of these and use the Shop library to explain some of the decisions. It's a bit of theory. I have talked about that Shop values are coming from the game theory concept of Lord Shapley developed the concept for the Shop values of game theory, and he won a Nobel Prize in economics in 2012. The way he explained, he initially developed it for, let's say, if a multiplayer game scenario to control an outcome, what he suggested is that the game's outcome will rely on the players that are currently playing in the table, and the way the developers of Shop library dealt with it in terms of machine learning explainability. So they are suggesting game is the output of the model. So game would be reproducing the outcome of the model, and the players in the game theoric scenario will be mapped as features that we are feeding into the model. So Shapley validates the idea that outcome of each possible combination of players, you need to consider the interaction between players as well when you are deciding how the output from the model has been developed. So how are we doing time-wise? Okay. So the first example that I wanted to share with you using the Shop library is for a regression model. And initially was thinking of, let's say, sharing using IPython notebook, but I've cropped out the results and shortened it in terms of explanation. So how can we use explainable APIs available from Shop to explain a regression model? The data set that I'm using for this example is a small data set of 506 houses from Boston, Massachusetts area. And this is a data set where you have information about the houses in that area, such as, let's say, crime rate, such as the crime rate. So if a house is placed in a town where, let's say, crime rate is high or low, information such as how many rooms we have in that house, what the house is. There are other information about the house, such as, let's say, pupil-teacher ratio, house around us. So let's say if a person is buying a house and he has his children that goes to school, having high pupil-teacher ratio might not be ideal. So you want appropriate of number of teachers to be there. And let's say LS stat is another important variable where if the house is in a neighborhood of, let's say, poor people, and so house prices might be lower just because of the environment around that corresponding property. And the final outcome variable for this regression model in this case is the median value of the property. So what we would try to do, we will process the attributes for the house and would try to predict the median value. So once a model is trained to predict the value, we will use some explainable AI toolbox to break down the decision-making process of the algorithm. So before modeling, what we could readily do is we can do exploratory data analysis to see the distribution of any of the variables that are available in the data set. So I have highlighted two variables in this case. One is the room number, another is the lower status of population. But for all the features that are available in the data set, we have a box plot on the left. One thing I want you guys to notice is the median value, which is the output value for this corresponding model. If you look into the median value of the property, the median value of the properties of this area is about, let's say, 22,000 US dollar and so on. And average number of rooms in this, 6 rooms per house and so on. LS stat is a value, lower status of population. If it is higher, it is poorer neighborhood. If it is lower, the number of poor people around that property is slightly lower. So if we initially look into the relationship of house price, which is in y-axis in the right side diagram with polynomial weighting, you would see that with increase of room number, house price is increasing. So there is a positive correlation between house price and room number. And if you look into the lower status of population, you will see that at the lower status of population, if it has higher value, the house prices are dropping. Yeah. So let's say these are the two things before doing any modeling. As a human observer of the data set, these are the things I would want the model to pick up when it's making its decision of a given house, whether this house should be of higher price or lower price. So let's have trained a random forest model. In this case with 10 estimators. So it has taken in all the input attributes. And with explainable AI tool sets such as Sharp, what you can do, you can create population level summary or local summary. The types of diagrams Sharp is capable of producing on the left side, this is similar to a feature importance plot. But the x-axis in this case, I do have a mean Sharp value that is actually representative of an average impact of a feature on model's output magnitude. So in this case, the output was the price of the house, and we say that the average house price in the data set that I'm displaying the results for was 22.38 thousand pounds. And the global diagram on the left is identified that LSS stat is the, let's say, most important predictor for this model's decision making of whether the house price should go up or down. And in case the second important feature was the number of rooms, then the third important feature by the model was the pupil-teacher ratio. Then there was, let's say, nitric oxide concentration. So it's about air quality, whether it's around an industrial area and so on. So the global summary plot is giving us some information about the top features for the model. With Sharp, you can also have a local distribution of the plot. And in Shapely, you would see that in this diagram, there is a midpoint of Sharp value of 0. And if I say my predictor in this case is the price of the house, in the local, this plot is called the B swarm plot. So if in my data set, I had got 506 houses, all of the houses will have a dot for each of the houses. And what you would see that, let's say, one of the properties with LSS stat value, and to interpret the B swarm plot, you also need to look into the color scale. And if your feature had a lower value, you will see the color blue. If your feature has a higher value, you would see the color red in these plots. So LSS stat, red color, which is indicating the high value of LSS stat, you would see that they are contributing in reduction in houses price by, let's say, as much as 5,000 US dollar. And if the lower status of population was, let's say, low, and you would see that a very low value of lower stat of population is contributing in increased price of 12.5 thousand pounds. I'm saying pounds, US dollar for this data set. So this gives you an understanding, these types of summary plots. If I want the house price to go up, to have the lower status of population to be low, if you look into the room number feature, you would see that the more the number of rooms we have in this property, the price of the house is going up, and it could go up depending on various properties are going up by various amounts. And so on. So with this, what you can do is new house that you are passing through this model, you can create a contribution table of what these houses price should be. So because this model has seen 506 houses and the population average of the house is 2.38, will start from that amount of money for that house price. What the model will do is it will increase from this baseline value up or down depending on the features that it is seeing and processing by the model. So the diagram that I have, the table I have this side is contributions table, and the table is a screenshot that I have taken from this explainer dashboard for this specific model. So what the model is suggesting, when it processed for this specific house, an LSS stat value of 5.57, what it has done in this case is, if you look into the houses that we have seen from this data set, the average LSS stat value for all the properties in the training set was about, let's say, above 10, 12. And this house that we are processing at this moment has lower value than that. So it has provided an impact of positive 3.81 thousand to the house's price. And then when it processed the next variable, room number 5.9, looked into the population average, that it has seen that more than 6 rooms are common in this data set. This room has lower value than the population average, and it reduced the house price by 2.49. So you may ask, like, how these effect value are being processed. So you then are going into the global summary plot that we have seen in there, and it is actually placing that average impact from the global summary plot. So it processes all the variables that are coming, and it adjusts various values, and it finally predicts that the house that you are seeing with these properties, the model is predicting that this house should be priced as 23.3 thousand US dollar. So by this way, you can see how, like, what features are making positive impact for the model, what features are creating negative impact for the model for this specific contribution. So with these toolboxes, I'm saying that, let's say, for the house price data set, you can tell that how much money you can raise up or down based on various features and so on. And it should give a bit better information in terms of, let's say, if you're going with your model to a stakeholder or a person that will be using this model, they can relate in terms of their human understanding whether the price should go up with this feature, prices should go down with this feature. And whatever the toolboxes that we have available, they are producing outputs. They are producing these outputs, and what I would say that this still requires a lot of user interface design problems. You have to make sure that stakeholder is understanding what you're trying to convey as a message from the models. These are organized properly in a user interface, and they are being dealt in a specific way. Kind of short in time, so I'll jump across the other examples. So this was a toy example, but we managed to deploy one of the dashboards for the Scottish sea farmers, which was a seafood innovation funded project. And we developed a fish health classifier for them. It was deployed on a cloud-based Heroku app. And I have a recent publication for a cybersecurity scenario where we had an intrusion detection model, and we tried to explain the decision-making process of intrusion detector using toolboxes that I just mentioned. Second example, I'll probably skip just because we are kind of out of time. And if any of you are interested, you can write to me. I should be able to share the slides, and I do have the Python notebooks for these. And in the slide, there are some links to the notebooks as well. For an image classification model, the way Shapely values work, we say that most of the neural network-based architectures, they are not inherently explainable. So there is a TensorFlow playground where you could, let's say, experiment around how various hidden layers or having additional layers, how it is impacting the decision boundary for a classification or a regression scenario. The example that I was hoping to share was from a convolutional neural network on the MNIST dataset, which has 10 different classes. The way to use the Shapely values in this case is, let's say, if you have a model that is a deep learning model and you have trained it, you use the API from the SHAP library called SHAP Deep Explainer. And you take the model, give the trained model in as the input, and you provide some background or test images so that it can be seen in terms of SHAP value. So let's say you have a test image of 9 fed to a convolutional neural network, and you have employed an explainer to explain how this 9 value is being on the 10 different class channels for this classifier. So the diagram that I have in here, if you see the activation of red in here, you would see that out of the 10 different channels for outputs, for the input 9, you have highest activation at 9. And there are a few other activations in other channels, but the highest activation is at the channel number 9. For a test image of 0, you may see that there is an activation for channel 0, channel 1, 2, 3, 4. So if you write a 6 with a loop like this, you may see some activation in the numbers channel, which has a loop like this. So you may see various activations, but out of the total activation that you are seeing, the model will decide based on the highest activation that it has seen on a specific channel. In the SHAP's official website, there are examples based on pre-trained models and so on. And in one of my recent examples, so I had a PhD student in Norwich who was working on precision spraying, and we used GradCam++ activation to, let's say, automatically label some spray deposits or droplets. So we used the activation map to produce an automated labeling of where it is on the area of it, let's say, in a sprayed zone under a gimbal sprayer that we have in the lab and so on. So you can deploy various layer visualization techniques to improve the network performance, to do some automated tasks and so on. I had 2 simple slides on counterfactual explanations. So as I said, we use counterfactual explanations in electronic health records. And it is a way of perturbing various variables. So this is an example from a stroke and no stroke detection model. So for a specific participant, if the person BMI is 34 and the model predicted that this person will have stroke, you could change, perturb that input to go in a range of values possible. And what you can suggest to the patient in that case is, let's say, okay, you need to reduce your BMI by this amount so that your risk for something goes down and so on. And the tool sets that I usually use for this type of, let's say, explanation generation is coming from Microsoft, and it's the DICE library. And with electronic health records, another type of explanations that I'm currently focusing on is explanation of time series data. is very important, and the type of participation that we are proposing in the project proposals that we are sending to HR, dealing with dynamic perturbation operator. And there is a reference for this technique. I think we have colleagues that are interested in time-series explanations as well. I'd be happy to talk to you guys and would be happy to collaborate if there is opportunity in terms of method development and so on. So it's one of the very last slides. There are a few other relevant research directions in AI. So data-centric development term currently using, where we are suggesting rather than training a model over and over again, when saturated accuracy, we go for analysis, tuning the model, we're suggesting tuning the data. So it's a concept NG, and he suggested that for the depleted state of model training, it's better to focus on the data that we've been trying to optimize the model by making them more complex and complex day by day. So there is another trend on AI auditing, the rise of the AI acts and laws. So Stanford had an AI audit challenge in October, where they wanted to, let's say, drill down large language models to identify. So there is such direction in terms of auditing and talking to models. So we need methods and tools for these systematic and tools. And the final set of research direction with explainable AI is, once you know that your problems, it's sometimes better to have good data than big data. Getting good data, people are suggesting, is if you have population representative synthetic data in terms of, and it also deals with the problem of, let's say, if somebody is comfortable sharing their own data and privacy aspect. Federated learning is another step that we are using to deal with user privacy. And let's say hospital, at the diagram I'm using in here, this research center has their own data. The way federated learning is working is you don't have to share your data, but you can share the model and so on, that you can have a global being developed. So some parting thoughts in this case is, it's a highly interdisciplinary field, and there are opportunities for various people to collaborate in terms of development or algorithm or method development. There are a lot of opportunities in user interface design, because you need to make sure whoever as the stakeholder is using that interface to get the explanations out from the model, get the right set of information out there, and you do not want to overwhelm the users. So I'm 1 minute up. As I said, this is an interdisciplinary field, and we can actually contribute in various directions. So there is a cheat sheet that I shared as the last slide. So a group from, I think I had the person's name on top, so they have given a pathway of, let's say, which way to go if you're trying to explain different types of environments. So that would be it from me. There are some resources that you will find. Thank you very much. Microphone. Thank you. Sorry for making it late.
Thank you very much, Tahmina. Do we have enough time, Alan, do you think, for a couple of questions? I know that there's a lot of people have got 4 o'clock meetings, but we'll just have a couple of quick questions. I knew Alan would have one because he works in Explainable AI. So over to Alan. Just a second, though.
So if you go back to the previous slide. Yes, okay. So the top right, there, the interpretable models. I read a really good paper by someone called Rudin, who was kind of saying how important interpretability is over explainability. And they put forward quite a convincing argument to say that explainable methods are simply bolting on another module on top of something that's already quite black box, and therefore creates more distrust instead of less. Do you have any thoughts on that?
Say that is making it less trustworthy. What we need is, let's say, because explainer methods are, again, a set of algorithms that we were trying to drill back to the black box model. What we need to have to build their trust is assessing or testing the explainer modules properly again. So it's, again, explainability to the explainer module, I would say. So I agree with the complexity, but you do not want to compromise on the accuracy that you can achieve with the neural networks or the state-of-the-art model architectures that we have. So I would not give up on the technological advancement for the sake of, let's say, interpretability from the intrinsically explainable model. Yeah. So you can find out a lot of complex relationship when you have a complex model, and you need to trust on the explainer method development in a way that it helps us increase the trust.
Okay, we'll make this the last question. So hang on a second, Alan. No, everybody's got 4 o'clock.
But just to say, the work on counterfactuals of time series, I have a colleague in Stockholm who's just published a really interesting paper on exactly that. I'll send it to you, and we can maybe have a catch-up meeting about that. Okay, thanks very much.
Do we have any last urgent questions? If we got any questions, please feel free to email Tahmina the questions, and let's just thank Tahmina one last time as well. That's okay. If we have any IDA announcements, we'll send them by email because Alan is just running out the door. Thank you everybody here for turning up, and thank you everybody online. Cheers. I'll sort it all out. Leave it to me.